know, every material body in nature attract each other. And very clearly we said, see, if it's a point object and this is a point object, mass m1, this is mass m2. If r is the distance between these two bodies, then these two bodies we can see attracting. This is very clear. High tide and low tide. Sometimes water level on the surface of the earth rising. Sometimes it's going down. This is because of gravitational force of attraction. Because suppose this is earth, moon is going in an elliptical orbit actually around here. So when moon come closer to the surface of the earth, this attraction will be more. So that lifts the water up. When it is going far, that attraction is reducing. That's why low tide is developing there. Clear? See, this is a very clear example. Then you may think why these two books are not attracting, or when we are standing near the other person, why we are not attracting. Okay, but you remember you are being attracted to the earth. If there is no attraction, you will fly off because earth is a moving body, rotating body. In a rotating body, if you stand, you will throw off. So earth is, you are being pulled by the earth towards it. So this is all very clear example. But in smaller bodies, we don't see that because this force of attraction is very, very weak. But if one body is very huge, other body is very small, very clearly you can observe this attraction. So according to Newton's law of gravitation, the force of attraction between these two bodies, F, is directly proportional to product of their masses and inversely proportional to square of the distance between them. If it is an extended body, we take center of gravity for that purpose. Okay. So this is a Newton's law of gravitation. Now M1 increasing, naturally force will increase. M2 increasing, force will increase. R increasing. Why this is R squared? That's another question. All other thing, okay. Why not it is R? Why not it's R cubed? Why it is always we are considering R squared? This is because, look here, attraction or repulsion or interaction between two bodies taking place due to exchange of some invisible particles. These particles we cannot see. And there is a new branch developed to study out of it. It's called particle physics. In particle physics, they say a body, a material body emit a kind of invisible particle, which is called graviton. Graviton. You don't have to study about it, but you should have that knowledge. Otherwise, you will always have a doubt why this object is attracting. So between two bodies, there's a graviton exchange taking place. For this, what example they're saying? Suppose a frictionless body. You and your friend standing at a distance. You are taking a brick and throwing to him. He catches it. While throwing, you will go back. That boy also will go back. See, this kind of particle exchange leads to repulsion, moving away. So whenever you see repulsion, this kind of particle exchange will be taking place. Attraction means you have a boomerang. Other person also having other person standing back to back. You're throwing the boomerang. So this boomerang, you know boomerang, okay, it will go and circle and come back. By the time it reaches him, he catches it. So when you throw, you move towards him. When he catches, he will also come towards you. This kind of particle exchange leads to attraction. So in the case of two material bodies, it gives out a particle called graviton. So this is happening like this, it is throwing, this is receiving it. So these two will come closer. These are all assumptions. Okay, we think it may be like this. Okay. Just before
what,
33.
What error is called here?
Roll number 33 came. Roll number 33. Some boy. Okay. Now look. From one point, if you're taking, see, particle can go all the directions like this. Isn't it? All the directions. So here, if you imagine a sphere, suppose radius of the sphere is 1 centimeter or 1 meter. Suppose radius of the sphere is 1 meter. This particle exchanging, giving out around 1,000 graviton. Imagine 1,000 graviton. So here, if we imagine a sphere that encloses the surface, we can see number of photons coming out here 1,000 and area that encloses at a distance 1 meter is 4 pi r squared. R means 1 squared. Then per unit area, how much it's coming out. This is called intensity or strength, how much it's coming out through that unit area. We can calculate phi by A. For example, 1000 divided by 4 pi 1 square. Now imagine same sphere, but 2 meter bigger. So here you have to imagine a little large sphere. How much is passing? How much graviton passing through this sphere? That is same 1000. Same 1000 again passing through this outer one. But now area increased. Area become now 4 pi 2 squared. That means per unit area now, number of photons passing will be reduced. Then that effective force will reduce. Example, this paper I'm keeping near a light, torch light. So here small area, more amount of light is falling. If I'm keeping it far, naturally that light is spreading. So now same area, amount of light falling is less. So that become less brighter. See, suppose I'm speaking, you are standing very near to me. Then your eardrum per unit area receiving more sound wave. So you feel it louder. But if you start moving, see my sound is spreading. Then your eardrum receiving less amount. That less I mean square the factor, it's decreasing. See, 1 become 2 square. That means denominator 4 will come. If 3 meter, if you are standing, per unit area, you are going to receive 1000 divided by 4 pi 9, 3 square. See, 9. So 1, 4, 9. Square the factor, that particle reception is decreasing.
So we just have to divide it by phi and the area.
Yeah, that's called intensity. You
Intensity.
understood? So that is the reason. So intensity, number of photons per unit area, number of graviton per unit area, receiving, reducing means then its effective force also reducing, isn't it?
Yes, sir.
Not only here, even sound, light, everywhere you can see this idea. That's what I told you. Near a bulb, keep this paper. You can see it's look brighter because more light energy falling in the unit area. Now this paper keep very far, then brightness reduce. But from the bulb, same amount of light only coming out. If I'm asking why this brightness reduced, then you will say, sir, look here, less amount of energy only falling in the same area. So naturally brightness will be less. Is it clear?
Yes, sir.
So from a point, you can see this is spreading. While spreading, unit area if you are imagining. So here I can show with the diagram that, okay? Look here. Here, if you're taking, this is a point. Here we are marking some area, some rays here like this.
So r square is the radius, right, in the formula?
Square of the radius, square of the distance, not radius, distance actually we can say. So this is a bulb, for example. Okay, you imagine a sphere here. Okay, a just transparent sphere, imagine here. It look very brighter. A lampshade, you know, lampshade, a spherical lampshade you put around the bulb. So if it is smaller radius, 1 centimeter, then you will see it is more brighter. Because imagine an area, you see, more light is passing through that. But around here, if you're putting a lampshade of little bigger one, you see, bigger one, then it won't be that brighter. Isn't it? See now, same area you imagine here also. Same area, if you are imagining, see, light is only less amount is passing through that. Here only one ray, not even one ray passing through that according to diagram. Is it clear?
Yes, sir.
Yes, sir.
Yeah. See, if you're marking like this, isn't it? See, here more light is passing through this point. More light is passing. See, 1, 2, 3, 4, 5. But here only 1 is passing. That means as the area increasing, square the factor, that energy passing through that area will decrease. That's why that effect, whether it is light, brightness will decrease, sound, loudness will decrease, electric field force will decrease, magnetic field force will decrease, gravitational field force will decrease. That's a common idea everywhere. So from a point object, square the factor, its strength will decrease. Okay, that's very important. So we can say intensity is inversely proportional to d squared. This is a general formula. Even 12th also, I'll recall this concept. That's the reason here we are saying when you're taking a point object here and point object here, mass m1, m2, they are sending graviton all around. As the distance increasing, the reception by the other body will decrease square the factor. So naturally, force will decrease. Clear? That's what we are saying here. This is R. Okay. The gravitational force of attraction is directly proportional to m1, m2 divided by r squared. Write down. Newton's law of gravitation. Every material body in nature attract each other. Every material body in nature attract each other. Every material body in nature attract each other. And the force of attraction between them is directly proportional to product of their masses and inversely proportional to the square of the distance between them. Inversely proportional to the square of the distance between them. Let M1 and M2, are the 2 point masses. M1 and M2 are the 2 point masses. Separated by a distance r. Then force of attraction between them.
Let M1 and M2 are 2 different points.
Let M1 and M2 are the 2 point masses separated by a distance r. Then the force of attraction between them can be written as F is directly proportional to M1, M2 by R squared. M1, M2 by R squared. Now F is equal to G, proportionality constant, M1, M2 by R squared. Here capital G is called gravitational constant, universal gravitational constant. Universal gravitational constant. Universal gravitational constant. Universal gravitational constant. And value of G is estimated as 6.67 into 10 to the power minus 11. Unit, look at G. Unit of G. F R squared divided by M1, M2. Force is Newton. Distance meter into meter, meter squared. This is kilogram into kilogram, kilogram squared. So we can say Newton kilogram to the power minus 2 meter squared. Or Newton meter squared per kilogram squared. Anything we can say. Actually, this value estimated by the scientist Cavendish, but you don't have to study that. There was before in the syllabus, it was there, Cavendish experiment, okay, to determine value of G. So this experiment Cavendish found 6.67 into 10 to the power minus 11 Newton meter squared per kilogram squared. So now, like this pace, I will continue all the chapters which we went fast. Okay.
Yes, sir.
So those who want to attend the class, otherwise you can collect the recording from someone and you can listen to that classes. I will continue until that whole portion over. Vacation I will continue daily.
Sir, this Saturday.
I will continue my class Saturday not Saturday, Sunday onwards. I will continue.
Okay, sir.
Okay. So those who are interested, you can attend. Already I gave these notes, everything to you. But if you want a detailed learning, you can come again.
Okay, sir.
Next one. Look. Next heading, Newton's law of gravitation in vector form. Newton's law of gravitation in vector form. Newton's law of gravitation in vector form. Look here. Here, M1 attracts M2. By Newton's second law, reverse also, a third law, reverse also happening, right? Every action, there is an equal and opposite reaction.
Yes, sir.
Remember, I have sent you one video. One person is going in a bike. It's funny video, but it
Yes,
gives
sir.
a lot of insight.
Yes, sir. Yes,
Two
sir.
children are usually teenagers, they do this kind of foolishness. They go in bike and there was a cow on the street. With the feet, he just kick it, but he forget Newton law. Because cow is too heavy. So how much force you are exerting, same amount of force you will get back. Without thinking only that boy, he pushed it. So sometimes physics knowledge is very, very important. That cow is much, much heavier than that boy. So when he kicked, the same force he is pushed away and he fell down on the other side. So every action, there is an equal and opposite reaction. So here same way, if M1 attracts M2, M2 attracts M1 also, reverse also. But even the forces remain same, acceleration will be different. I told you, suppose this is a 100 kilo body, this is a 1 kilo body. So 100 kilo body attracts 1 kilo body towards here. Say that force is, say for example, 100 Newton, for example. After calculating, I got 100 Newton. If you want to calculate acceleration, force by mass, 100 by 1 kilo. With this 100 meter per second square, this body moves here. But this body, how much force is going back towards it? That is A of 100 body, okay? Force is same force they will experience, but mass is 100. So only 1 meter per second square. So this is while moving 100 meter per second squared here. This is going only 1 meter per second squared here. So this movement usually we don't notice because 100 times faster this is approaching here. So before this is moving, the other one will reach near to it. That's the reason when you're holding an apple above earth, apple attracts the earth. Earth attracts the apple. Same force. But acceleration when you're calculating, acceleration of the earth is very, very smaller because force by mass. Mass of the earth is very large. But mass of the apple is very small. So force by mass, acceleration will be very large. That's what when you're dropping, you see apple is moving, earth is not coming up. Actually, they both are coming closer, but we don't see the movement of earth. Is it clear?
Yes, sir.
Yes, sir. Yes, sir.
Yes.
Yes, sir.
So here by Newton's law of gravitation, we can say, see, force acting on the body 2 by the mass 1. This is the way it's representing. Force acting on M2 by M1. C equal to, its magnitude is G M1 M2 by R squared. This is a force. But we have to indicate the direction. Force acting on 2 by 1. Which direction 2 will move?
Towards 1.
Towards 1.
Vector
So that
R1
arrow you indicate there. So usually this is represented by a vector 2 to 1. You see, unit vector. Unit vector means 1 unit value. Okay, so we can mark here unit vector 2 to 1. So this symbol will tell you this body is going towards 1. That means body 1 attracting 2 towards it. That's the meaning of it. Reverse also you can write. Force acting on 2 by 1. Sorry, force acting on 1 by 2. Reverse. Force acting on 1 by 2. Now what happens to 1?
1 will attract to 2.
1 will move towards 2, isn't it? See, force acting on 1 by 2. This is force acting on 2 by 1. Okay, so this will go to R1 to 2. See? So same way we can write here. G M1, M2 r squared. That doesn't change. Magnitude doesn't change. But direction, unit to vector. Unit to vector means value 1. That only indicating the direction. Okay. And where it's going? 1 to 2, right? It's going from 1 to 2. That direction you have to indicate here. Which direction that object is going. That direction force acting. Is it clear?
Yes, sir.
Yes,
Sir, what did you say last? Which direction?
Which direction one is going?
Yeah,
Towards 2.
Towards 2. Towards 2, that's the direction 1 to 2. Clear?
Vice versa, right?
Yes.
And a force acting on 2 by 1. Which direction then 2 moves?
Towards 1.
Towards 1. So 2 to 1. See, 2 to 1 body is moving. That's the direction of force, right?
Yes, sir.
If I'm pushing you away, you will not come to me. Or if I'm pulling it towards me, you will not go away. Which is the direction force acting, that direction only you will move, right?
Yes, sir. Yes, sir.
So look at the object, which direction it's moving. That direction you mark there. That's all. Clear?
Yes, sir.
Right now. Now, in vector form, right, the force acting, draw the diagram and write. The force acting on the object 2 by the object 1. The force acting on the mass M2 by the mass M1. The force acting on the mass M2 by mass M1. So write force acting on 2 by 1, F21. C equal to, this is the magnitude, G M1 M2 by R squared. Now look at 2. 2 moves towards 1. R2, 1 you mark. Second one, force acting on M1 by M2. That means F12. Then mark this. Those who joined late, I will not give attendance, okay? Is it over?
Yes, sir.
Yes, sir.
You understood
Yes.
this? Anyone has doubt?
Yes, sir. No.
Okay. Next, acceleration due to gravity. Acceleration due to
Sir, this
gravity.
acceleration is on Earth.
Acceleration due to gravity. Look here. Let us calculate acceleration on a body due to gravitational force. Because whenever there is a force, there is an acceleration. Force by mass. Here we are calculating when Earth attracts a body, how much acceleration it gains. That's what you're going to calculate here. Okay. Suppose this is mass of Earth, ME. Around 6 into 10 to the power 24 kilogram will come, mass of the Earth. Above this, I'm keeping an object of 1 kilo body. Now we are taking center to center here. Always distance you have to measure center of this body to center of this body. Radius of the Earth 6,400 kilometer. And this radius, say for example, a 1 kilo body means very small radius compared to the Earth. So that I'm neglecting. Otherwise, you have to take 6,400 kilometer. Okay, plus this may be 1 centimeter height. That 1 centimeter, how will you write? 0.01 meter.
So for what you're saying, this one, this value.
Radius, distance from center of the earth to center of this body.
Okay, sir.
6,400 kilometers is the radius. And from here to here, 1 centimeter, radius of the body. Then that may be 0.01. Whether you add it or not, it will not make any difference, right?
Yes,
Yes,
sir.
sir.
So that's what I'm just taking radius only here. I'm neglecting that small part. So 6,400 kilometers is the distance. Now let us calculate force of attraction between these two bodies. F is equal to G m1 m2 divided by r squared. F is equal to G, gravitational constant, 6.67 into 10 to the power minus 11. M1 is mass of the earth, 6 into 10 to the power 24 into mass of the body 1 kilogram divided by radius 6,400 into 10 to the power 3 whole squared. If you solve it, you try to solve it later, your answer will come 9.8 Newton. That means a 1 kilo body you keep just above the surface. Earth attract the body with 9.8 Newton force. And body attracts the earth also 9.8 Newton force. If you are calculating acceleration of the earth, force on the earth divided by mass of the earth. So force on the earth is 9.8. Mass of the earth is 6 into 10 to the power 24. You know, if 24 goes numerator, that will come 9.8 by 6 into 10 to the power minus 24. So 9.8 by 6. Can you just tell me the answer using calculator?
This is acceleration of Earth.
Acceleration of the earth. First we are calculating. Okay. Can you tell me the value? 9.8 by 1.6. 9.8 by 1.6. 6.125 into 10 to the power minus 24. That means 0.000000000 24 zeros. Then 6 will come. 23 zeros and 6. Such a small value. So we won't see even earth is moving. Clear? That's what we are not considering acceleration of the earth. But let us calculate reverse. Acceleration of this 1 kilo body towards earth. Let us calculate. Okay. So force remains same again. Acceleration of body towards earth. Okay. Force by mass of the body. Force is 9.8. Mass of the body is 1 kilogram. So acceleration is 9.8 meter per second squared. So this 1 kilo body moves towards the earth with an acceleration of 9.8 meter per second squared. Now I'm keeping here suppose 2 kilo body. Calculate the force. So this is for 1 kilo body. 2 kilo body means this one become 2. That's only change, right? Isn't it?
9.6.
Instead of 1 kilo, I'm keeping here 2 kilo. All other factors same. G, M1 is same. M2 only changing. Radius also same, right?
Yes, sir.
So here, this much portion, I already got the answer, 9.8. So instead of 1, I have to put here 2. Isn't it?
Yes, sir.
So this is the force acting on 2 kilo body. Then acceleration of 2 kilo body, 9.8 into 2 divided by mass of the body, 2. So 2 cancel. See, acceleration remains same. So your mass increasing, proportionally force also increasing. So force by mass remain same. So acceleration remains same. Keep your 3 kilo body. Then this will be 3. This will be 3. Division will be 3. Answer will be 9.8. Keep your 100 kilo body. Then this will be 100. This will be 100 divided by 100. This will be 9.8. So whether it is 1 gram or 1000 gram, you keep above the surface of the object, release it, that travel with same acceleration. That's the first thing to understand. So this is a constant body, irrespective of mass. Because more the mass you keep, more the force acting. More the force acting, force by mass always remains constant. Is it clear?
Sir, this is only this is only applicable in vacuum, right?
In vacuum only we are discussing, because earth friction is negligible. I'm not talking about small paper or something like that. Heavy bodies between earth and a 1 kilo body. So their friction is neglected almost, isn't it?
Yes.
This is happening in vacuum. In the case of feather and all, friction of air will be affected. Now this experiment you can try at home. Take a notebook, okay? Keep a small paper, drop it at the same time. You can see book will reach the ground first. Then you may doubt, sir told everybody will reach same time, from same height. I'm not wrong, because you did not protect the lighter body from friction of air. Heavy body, friction is immaterial. It ignored
Sir,
the
one video is there for that. Like,
keep the smaller paper above this book. We can try this. It's very interesting then. Just drop it. Now this book protects that small paper from the friction of air. Down if you are keeping, then people will argue this book is pushing the paper. Keep above. So this book is not going to push the paper. Keep a heavy book like this. Keep a paper. So first you keep together, same distance, drop it. You can say book will reach first. Then keep the paper above and drop it. Both will reach same time. That means this book will overcome the friction. So paper also not affected by friction. In such case, both will reach same time onto the floor. You can check this.
Sir, in the formula R square 6,400.
Understood. If they are saying height is around 6,500 kilometer height or 2,000 kilometer, then it is considerably, there will be a change. Otherwise, flight and all very small, only 3 kilometer, 4 kilometer height only flight is going. Is it clear?
Yes, sir.
So their gravity will not have any change. So in such cases, we can neglect. That's what here I'm marking. If H is very, very smaller than R, that means we are dealing with heights around the surface. In that case, H can be neglected. If you did not understand, ask me right now. Later on, if you ask, I will not be able to clear your doubts. Is it clear?
Okay, sir, explain it again, sir.
Which one? This H.
Yes.
Suppose here you are keeping a body at a height of 10 meter. Okay? Do you follow?
Yes.
Now calculate G value. You calculate using the formula. Tell me after calculation. 6.67 into 10 to the power minus 11. Mass of the earth is 6 into 10 to the power 24. Radius 6,400 kilometer into meter.
Yes.
1000 plus 10 meter and take whole square
Okay.
and calculate the value and tell me the answer.
Okay, sir.
I'm waiting for your answer. You calculate, then only you will understand. Otherwise, if I
sir,
keep
1
on
minute.
speaking, you won't understand.
Yes, sir.
What is
Yes,
the
sir.
answer?
Sir, around 10, 9.8.
9.8.
0, yeah.
Now without a 10, you calculate.
Okay, sir. Sir, it's something around 7.
Same, isn't it?
Yes, sir.
Same answer will come. That means
Yes,
this
sir.
10 does not make any influence over here because this is a very small increase. So value will not have any change there.
Yes, sir.
Clear?
Same
So
answer. Yeah.
is it necessary for this 10 to add and making this so complicated?
No, sir.
So that's what I'm saying. Such cases, see, if H is very, very smaller than R, H can be neglected.
Okay.
That means when you're
Understand, sir.
dealing the heights like 10 kilometer, even until top of the Mount Everest, the highest
Yes.
point on Earth's surface is Mount Everest. That is around 9 kilometers,
Yes,
something
sir.
like comes.
Yes, sir.
Clear?
Yes, sir.
Even up to
Yes.
that height, if you go also, gravity will not have much change.
Okay.
It will be a negligible change, but that won't be noticed. Clear?
Yeah. Yes, sir. Thank you.
That's why smaller heights and all, H can be neglected. Here we no need to add, we can neglect it. Smaller height. Clear?
Yes, sir. Thank
yes,
you.
sir.
So if h is very, very smaller than r, then h can be neglected. Then formula can be written as g is equal to gme divided by r squared. So this is a formula commonly we use everywhere.
Sir, here you R is equal to big R plus H. How did you make that? Just can you say again? R plus H.
This one.
Yes.
What is this r?
This is height
Distance
plus
between,
radius.
distance between centers of two body having force, right?
Yes.
So from this center to this center, what is the distance?
H.
H from surface to here.
Okay.
From center to here, what is the distance?
R.
R.
Then from surface to M.
R plus H. R plus H.
Yes.
R plus H. Isn't it?
Yes.
So this R I am replacing by R plus H.
Okay, sir.
That R plus H is coming here, right?
Clear, sir.
Next. So here, finally, we got G is equal to GME divided by R squared. Okay. So this expression, right? This expression shows that acceleration due to gravity is independent. This expression shows that acceleration due to gravity is independent of the mass of the body, falling towards it. Mass of the body falling towards it. Clear? So this formula applicable to smaller heights. Larger heights come, formula we have to use G is equal to GME divided by R plus H whole squared you have to use. Is it clear? Formula difference between this formula and this formula.
Yes, sir.
No. You understood, right? All of you.
Yes, sir. Yes, sir. I understand.
Next, variation of acceleration due to gravity with respect to radius of the earth. Variation of acceleration due to gravity with respect to radius of the earth. See, earth, even though we say it's a huge sphere,
So what is
it's
the
not
heading?
exactly sphere.
With respect to
Radius of the earth. See, normal concept, everyone say earth is a huge sphere. This is an approximation. Actually, earth is polar region slightly compressed, equator region slightly protruded. That's the shape of the earth actually. Okay. So if you're marking from center, correct measurement if you're making from center to here if you're taking, you see, center to polar region, radius will be say RP I'm marking. Okay. And center to
Yes, sir.
equator, this I'm marking RE. Here RE is greater than RP. Okay. Capital R, we'll make capital R because radius, right? This is RP and this is RE. RE, isn't it? So here RE is greater than RP. We know G is equal to GME by R. Okay. GME by R squared. This is G. Any doubt?
G.
Here
No,
G is constant, M is constant. So G is inversely proportional to R squared, right?
Sir, R square is the distance, right?
Radius from here
Yeah,
to here.
radius. Sorry, radius.
Right. So here if RE is greater than RP, then G at the equator is less than G at the pole, isn't it?
Yeah, sir.
That's all. That means when we travel from equator to the polar region, value of G slightly increasing, very small change. G increases. in this direction. Equator to polar region, G increases. Have you finished?
Yes, sir, I've finished.
Next, anyone has doubt in this?
No, sir.
Next. Calculate mass and mean density. Calculate mass and mean density of the Earth. Calculate mass and mean density of the Earth from the following data. From the following data. Mean density means, see, Earth is not a homogeneous material. It has rocks, it has sand, it has water, molten lava. That's what average density or mean density we are considering. Okay, calculate mass and mean density of the Earth from the following data. G is equal to, this is given data, 6.67 into 10 to the power minus 11 Newton meter squared per kilogram squared. Then radius, R is equal to 6.37, 10 to the power 6 meter. It's approximately 6,400 kilometer, but here the value they have given. G 9.8 meter per second squared. Find the mass and mean density. First, let us calculate mass.
Sir, capital G is
Gravitational constant.
gravitation. Yeah.
G is equal to GME divided by R squared. Any doubt?
No, sir.
No,
Now, mass of the Earth is equal to GR squared divided by capital G. Substitute. Mass of the Earth is equal to G is 9.8. Radius 6.37 into 10 to the power 6 whole squared. Mass of the Earth divided by radius. G, this G. 6.67 into 10 to the power minus 11. Here I'm substituting, okay? 9.8 into 6.37 into 10 to the power 6 whole square divided by 6.67 into 10 to the power minus 11. Calculate and tell me the answer. ME. Mass of the Earth. For the time being, use calculator and tell me the answer.
Sir, can you explain the second part? ME is equal to 9.8, the substitution.
G is 9.8.
Yes.
R is 6.37 into 10 to the power 6, right?
Yes.
Substituting whole squared.
Okay. I thought we were both adding G and M.
G is, see, M is equal to G into R squared by G. Small g
Yes.
is how much? This
9.8.
one, 9.8. R is 6.37 into 10 to the power
6.37.
6 whole squared. Small
Okay.
g is 6.67 10 to the power minus 11.
Okay. I thought we were adding ME and the other G. We're substituting them. It's okay.
Sir, is it 6.24 into 10 raised to 24?
6.2 into 10 to the power 24. Yeah, 6 into 10 to the power 24 approximately, isn't it? Just before we study, right? 6 into 10 to the power 24. 6.2
Yes.
into 10 to the power, no problem. Because such a heavy mass, right? Now, did you understand this?
Yes,
You
sir.
can write approximately. If you know by heart, you can write 6 into 10 to the power 24. You will get the mark. 6 into 10 to the power 24 kilogram. Okay? Any doubt?
Yes. No, sir.
No, sir.
Next one, G. Next one, density. Mean density. How will you calculate density? Density is equal to mass by volume. Density is equal to mass by volume. Or density is equal to mass of the earth is m. Volume 4 by 3 pi r cubed. Isn't it? Tell me.
Yes, sir.
So
Volume
rho
of
is
air.
equal to 3m divided by 4 pi r cubed. Mass just now we calculated. 3 into, what is mass? 2 into 10 to the power 24, right?
Yes, sir.
6
6
into 10.
6.
That is 6 only.
6 into 10 to the power 24 divided by 4 into 3.14. R cubed. What is R? 6.37 into 10 to the power 6 whole cubed. Isn't it? What is the answer?
What's the answer?
What is the answer you got? Three into 6, 18. 10 to the power 24. 4 into 3.14, how much are you getting?
Sir, 5.5 into 10 raised to power of
Sir,
3.
Answer you're giving?
is
5.5
into 10 raised to 3
Correct.
per meter cube.
Yeah. 5.54 into 10 to the power
10 raised to the
3
power 3.
kilogram per meter cubed. This is the answer.
Yes, sir.
Okay. Next question. See this formula, G is equal to GME by R squared. We have derived it for Earth surface. Okay, just 1 minute. From school one call. So here, this we have derived for Earth, but not only for Earth, every planet it's applicable. If it is for Moon, the only change come instead of mass of the Earth, we just put mass of the Moon, and here radius of the Moon. So this is G of the Moon. So any planet, if for Mars, take it Mars. That's all. Is it clear? Write down. Acceleration due to gravity at the Moon surface acceleration due to gravity at the moon's surface is 1.67 meter per second squared. Acceleration due to gravity at the moon's surface is 1.67 meter per second squared. If radius of the moon is 1.74 into 10 to the power. So same formula we can apply here. Mass of the moon is equal to okay, here this m, why I'm not writing, because later on you will study mass into mass, like that you will read. So just leave it, you understand that. Okay, this mass is equal to gr squared divided by
G.
capital G. Gr squared divided by capital G. So G is on the surface of the moon, it is 1.67. Radius of the moon 1.74 into 10 to the power 6. Universal gravity constant same everywhere.
Sir, 1.74 into 10 raised to 6 the whole square. .58 into 10 raised to 22 kilogram.
Yes. 7.58 into 10 to the power 22 kilogram. Okay. Next question. See. First of all, understand, suppose this is Earth. On the surface of the Earth, weight of the body is mg, right? Mg is a weight. Force acting on a body towards the Earth is known as mg. Am I right?
Yes.
Same body, if you're
Yes,
taking
yes.
on the surface of the moon, force will decrease, right? On the surface of the moon.
Yes.
M
Yes.
remains same, but
Yes.
G will change, isn't it? G of the moon will
Yes,
come,
sir.
right?
Yes.
So this will give you weight on the surface of the Earth. This will give you weight on the surface of the moon. This weight changing just because of gravity changing, that pull changing. Otherwise, mass of the body remain same. I think you know about this idea, right?
Yes.
Yes,
I
sir.
know.
Yes.
A body weigh, right? A body weigh 90 kilogram force, kgf. This is a unit. 90 kilogram force on the surface of the Earth. On the surface of the Earth. That means this is mg. On the surface of the Earth. How much will it weigh? How much will it weigh? How much will it weigh on the surface of the Mars? This is Mars. How much will it weigh on the surface of the Mars? Of mass of the Mars, okay, of mass 1/9 of mass of the Earth. And its radius is 1/2 times, half of the radius of the Earth. Half of the radius of the Earth. This is a question.